So now let's talk about some hazards associated with earthquakes, which I'm sure you're aware of some. Hopefully we'll get through them all. And so we want to also talk about, and I mentioned a little bit in the previous video at the end, is what is impacting the amount of damage that we see. And so what we can see is that there's some obvious ones like the size of the earthquake. There's a relationship between the amount of damage typically and how big the earthquake is. That seems to make some sense. The distance you are from the earthquake seems to make some sense for sure. So the farther away you are, the less. And that can be from the focus. So now we're talking depth, remember. If an earthquake occurs near surface, more energy, it can cause more damage. If it's deep, it loses energy as it propagates toward the surface and can be less destructive. We can also do duration of the earthquake, and this is how long does the ground shaking last. Now, if I remember, I will add a video to the first page there that shows how we can get ground shaking that occurs for, let's say, 3 to 5 minutes. Some earthquakes last for a couple seconds, or 10 seconds, or 20. But with these really big ones, sometimes it's maybe curious, how do you get the ground to shake for that long if the rocks slip and break and rebound? What we tend to see is for these big quakes, they occur at these big boundaries, and the contact where the two plates are touching is huge. It is deep and it is long, so it can run for hundreds of kilometers. It doesn't all fail at once. And so we get a slippage along a part of that fault, which initiates energy waves. But that slippage then pushes against the plates a little further down where the contact is and causes that to slip, and we can get this kind of chain reaction. So we get slip, 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 and every slip gives off energy. So we can continually shake the ground from an earthquake that we would still say the epicenter occurred where the initial rupture happened, the first part, right? So that's how we can get long ones, and hopefully, if I remember, I'll put that little video up. Okay, what else? Population. So when we talk about damage, a lot of times it's not just structural, it's people. So there are death tolls that or people that are injured, and so there's a lot of people, your potential for a high death toll is there. Less people, right? You could have the biggest earthquake ever, and if there's 2 people, I had the biggest earthquake ever and 2 people died, doesn't sound like a lot. Well, there just wasn't a lot of people there, so that can certainly play a role. We talked about the geology or the ground material, so that plays a role in how it reacts. How buildings are built and constructed plays a role. And a little weird maybe, but the time of day, because of where people are. And so if freeways collapse and it happens to be rush hour, you can get more damage that way. Or if people are all at their office and buildings collapse or things like that. So certainly that can play a role also. All right, so what are the effects? So we certainly get ground rupture. So what does that mean? Well, it means that you can, but not always, when the earth when there's an earthquake, we get slippage, and sometimes that feature can be shown at the surface. And here we can see there's a sloping surface here. We would call this the fault plane. So this block is up, this block is down. It kind of looks like this little diagram here. And because of the block that's above the fault plane, that's this guy, went down, normal fault, right? So then I could tell you that there must be some tension here. It's pulling this place apart. This is why the rocks behave this way and formed a normal fault. And so, of course, depending on where your structures are, if there are cross faults that are moving at the surface, that can cause damage for sure. So it can be up and down, it can be side to side. Here you can see there's a strike-slip fault here because the material of the rocks have slid past each other. There wasn't really any vertical motion in something that happened here. So that's definitely a problem when we have structures on top of faults like that. The other thing that we could talk about is what's called liquefaction. And there is a little clip on the page that shows you kind of how that works. But the quick and dirty story is that this occurs mostly near coastlines. And look, we have plate boundaries near coastlines, right? California, the east coast of South America is a big subduction zone. The reason that it happens near coastlines is the water table. So water is stored in the subsurface, right? Rain hits the ground, it sinks in, it actually collects in the ground. And so we need water that is basically stored in the open spaces of this loose sediment. We need it to be close to the surface. Because when the ground shakes and we have loose sediment, they bang into each other and they actually squirt the water upward. And so although the ground here is dry and stable, if the water is close enough to the surface and the ground shakes enough, the water will rise up here and turn this dry stuff into wet, and it acts kind of like a quicksand and it becomes unstable, and we have some issues once again with structures that might be built on top of material that behaves that way. So what do we see? Here's some examples where this is a store of some kind, and this is the top of the door, so the door goes down into the ground here. So this store actually sunk down into the ground maybe 4 or 5 feet because the soil turned to a liquid here. In the Alaskan earthquake in 1960, oh crap, did I forget that? 64. The ground shook and actually flowed almost like a mud flow because there was a slope, and because it turned into a liquid, gravity's pulling it down slope and your house comes with it. So definitely an issue. And of course, near Alaska, we're near the coast where this happens, so the water table's near the surface. Another example where we had these big structures where the structures themselves didn't collapse, but they actually tilted over because of liquefaction. The surface that they were built on became unstable, and they basically sunk into the ground, and in some cases actually fell over. Other issues we get with earthquakes, and this also is dependent on where the earthquake occurs, but we get tsunamis. And tsunamis are waves that are generated when there's displacement, typically in the oceans, but it could happen in a lake, a big body of water. The idea is we displace water, and so with earthquakes, because we can have a vertical motion up or down, we can displace a large volume of water. And so typically where two plates are interacting with each other at convergent zones near a coastline, where they're actually touching is 100 maybe miles off the coast, so it's under the ocean. And when we have these big ruptures along the convergent plate boundaries, we can get some reasonable uplift here, maybe 10 feet. Now, 100 miles from the coastline, the water's deep here. So I'm moving up a huge column of water. Maybe it's 4,000 feet deep, and I am lifting that up. That's a lot of mass. And what happens is it rises up and falls down, and it propagates out in all directions, and it can move fairly quickly. And so as this huge wave starts moving toward the coastline, it actually gets even larger as it gets closer to the coast, and that has to do with the depth of the water. It's faster, but lower in deep ocean, and as it gets closer to the coastline and the depth of the water gets shallower, the wave kind of rises up. And so we can get these really big waves that impact the coastline and cause lots of damage. So certainly there's been some examples. In 2009, there was a big earthquake. No, I'm sorry, 2004. Oh, I can't remember my dates. 2004 in Indonesia, there was a very large earthquake and a just crazy big tsunami. And the tsunami actually did more damage and killed more people than the earthquake itself. It was ridiculous. And then in 2011, there was a very big earthquake in Japan. Both subduction zones, both happened under the ocean, both create a big tsunami wave, and they cause lots of damage. So they can be very big, very fast, and of course as they get closer to the coastline, like I said, they tend to grow taller and slower, and they surge in, and sometimes they can surge in, miles. And so we get this kind of, they're fast and furious out here, but the height of the wave isn't that big. But as they get closer and the depth of the water, the idea is that because the wavelength is so big, the front of the wave starts to slow down, but the back of the wave is still a mile away and it's moving super fast. It kind of crushes it, it piles up. And we can get these really big waves that impact the coastline. This is just a little example of a wave that hit the shoreline here and it sheared off all these trees. So there wasn't people here, or there was very few people here, but it impacted the coast here and sheared off waves. And one way that they determined how big the wave was where all the trees were sheared off, and some of them were hundreds of feet above the water level. So they can be pretty big. Here's kind of what I was talking to you about, the two big earthquakes that have happened recently that had a huge tsunami, and you can read more about those there. What else we got for you? So landslides, another impact. So look, when you shake the ground, unstable ground can move. So if you're in an area where it's pretty steep, and look, where plates collide, they tend to crumple the earth and cause mountain building, and so it tends to be steep. And so failures are not uncommon when we have earthquakes. In some places more than others, and as an example, in 2015, two plates are colliding here in Nepal, but there's no ocean. They're two continental plates, which means it's super steep. And there was thousands of landslides that were generated from this, and so they did lots of damage. So another factor to keep in mind. Fire is also a problem. So ground shaking breaks gas lines, and then a spark, boom, you get a fire. Water lines are also broken, and so then you get issues with trying to put out the fire, so that's a problem. Talking about what material you build your building on. This is a very generic kind of diagram, but it's showing you that bedrock, which we're going to say is any solid rock, and that could be igneous, metamorphic, or sedimentary, those do the best. So when you can tie into bedrock, the ground, they're so compacted that energy moves through there very efficiently. But sands and gravel, so they're sediment, not so good, and soft mud, the worst. And so depending on where things are built, this diagram is illustrating why during some San Francisco earthquakes, most of the damage occurred here in what they're calling the Marina District in some places. That's because this is all muds. It's bay muds that was kind of dumped here to expand the coastline, and that's where most of the damage was because of the material. This is just another diagram showing you the same thing. Some weird stuff can happen, and I don't really need to focus too much on this, but sometimes the height of the building matches the frequency of the waves that move through and causes some weird damage. An example, of course, is in Mexico City. One of the reasons there's a lot of damage there is twofold, but the big reason is that they're built on this yellow material, which is ancient lake beds. Lakes are quiet water environments. They're mudstones or muds. So if they haven't had time to turn into mudstones, it's a lot of mud. And they built their city on that. So when the ground shakes, it is amplified because of the type of material that's here. And you can check out a little more there from the link. Okay, here we go. Ready? Some prediction methods. So look, can we predict earthquakes? Maybe the word prediction is not a good one. We forecast. It's kind of like the weather. We say, hey, in 5 days it might be rainy. So it's hard to say when an earthquake will happen exactly. But we know that they're going to happen where there's plate interactions. So at least I can tell you, hey, Kansas, you're safe. But California, you're not, because I know there's stress there, so I know there's going to be an earthquake. But to tell you when, like tomorrow at 5 p.m., that is super tough and maybe impossible. But we can do some things. So there's a few things we'll list right here, and some are a little weird. But a foreshock, which means a small earthquake before a big one. But you don't really know that until after all of them are done. You might get a 5.4, and that's it. You're done. But you might get a 5.4, and then a 6.2, and then a 7.5. And you'd say, wow, those were, foreshocks before the big shock, instead of having aftershocks where you get smaller ones that happen, beyond that, after the event. So those are some things that can tell us about it. Pre-seismic uplift, which means, remember we said the rocks deform. And so if you get some compression or tension and the rocks are actually bending and bowing, sometimes we can determine that and say, hey, there's a change in the surface. Maybe there's an earthquake coming. Some weird stuff like water level drops or radon gas emissions are related to the rocks kind of fracturing slightly before the big event, which when you fracture rocks, you can increase the porosity and water can move weird places, or you can release gases that are trapped in the rocks. Even some cases we could argue that there's some strange animal behavior, like, Horses run out of barns, dogs barking, birds flying away. Those are not very, that one's not very scientific, but you know, anecdotally we hear some stories like that. For long term, we really are still looking at an average. And so that's kind of what this trenching idea is that if I can find a fault and trench across it, as long as I have some datable material, and a lot of times some soils are carbon rich, I can figure out how many times this fault has moved. And then, of course, because I know dates, I could say, look, there's been 3 faults in 300 years. So on average, this fault ruptures every 100 years. Now, does that mean, of course, it's going to happen every 100 years? Well, no, but if it hasn't happened for 120 years, we're overdue. It's probably going to come pretty soon. Or if we just had one and it's 2 years later, it's probably not going to happen, right? We need stress to build for sure. So we can measure some of these other things with instruments. And of course, if they increase or change, we could argue that something might be happening. This seismic gap story is a little counterintuitive, but the idea is that where there's a gap in seismicity, which means there hasn't been many earthquakes, in a place that I would expect earthquakes to happen, we would argue that that place is the place where the next earthquake might occur. So I know this is a weird diagram. I don't even know if it's the best, but this is a big strike-slip fault. And it's similar to the strike-slip fault in California. And this stress, so purple is low and red is high. What they saw was that when there was an earthquake at a certain location, it reduced the stress right where the earthquake happened, but it increased the stress kind of next to it. And so we got earthquakes and earthquakes and earthquakes, so we were releasing all the stress here, but this didn't move. This didn't move. And so the argument is that the place where it didn't move, or it didn't rupture anyway, there's still stress being applied there that has not been released. So if I have a long fault line and I have, 50 earthquakes on the eastern end, but on the western end I have 0, yes, the eastern end might have a small earthquake, but where am I worried? I'm worried about the western end where there's a lot of stress just continually building and not being released. Yes, there might be some small earthquakes that happen on the east end, but the west end, that's where the big one's going to happen. And I'm going to say there's a chance that a big one's going to happen on the western end that's a lot higher than the eastern end. Maybe 50% chance in the next 10 years that there could be a 7.5 magnitude earthquake. This is the kind of predictions you're going to get from scientists. It's on this part of the fault, in the next 10 years, there's a 35% chance of a 7.5 earthquake happening. That's as good as we're going to get. And I don't know that we'll ever get better than that because of the complex nature of how the plates interact and all that. We understand some stuff, but it's really difficult to figure out all the little details, and it's super complicated. Now, this is not necessarily a prediction. It's kind of a warning system, but I threw it in here because it tells us something about some ways to reduce damage. And so the shake alert was very prominent in Japan, where there's lots of earthquakes. It is basically a system that can detect the P waves. So remember, the P waves are much faster than the S waves. They arrive first. They don't do much damage. And so an earthquake happens. We have 2 waves racing across. The P wave gets here. As soon as it's sensed, we send a signal which travels much faster than the waves themselves. And that signal goes to some processing station, which then sends an alert to your phone if you live in the area. And then I can give you a little bit of a warning and say, look, the lag time, remember, between the two, maybe it's 10 seconds. I could tell you, hey, you have 10 seconds before the ground shakes. That might be enough to cover, right? Duck and cover, because look, although I didn't mention this, one of the real kind of reasons that there's a high death toll in any earthquake is not that the earthquake itself is killing people. They're not falling into big crevices. It's buildings. Buildings kill people because they fall and they crush you. So if I can get people to protect their heads by ducking under something strong, or get out of a building, if I gave you 20 seconds and you were close to a door, I can save people that way. And so we want to give you a warning. This is what the shake alert is. And I think it's just started in California, And so it has some benefits. It's not a predictor in that it can't tell you it's going to come tomorrow, but it can give you basically a little warning. Now, there is a little sweet spot here. If you're really far from the earthquake, it doesn't matter because there's no ground shaking. You're too far. And if you're right on top of it, if my city was right here, the lag time's too short. I can't tell you, hey, you have 0.3 seconds. It's too late, right? So there is a sweet spot, distance from the earthquake, where there's still some damage that can occur, but I can give you a 10 to 30 second warning, and that can be useful, right? Okay. I'm sure there's other stuff, but more warning system stuff. I think I threw this in here just because, do we get earthquakes in Arizona? We do. There's been some reasonable ones, like 5s up in Flagstaff area. And of course, because Yuma is close to the San Andreas Fault here, you could see the reason that it's got a high probability of earthquake is that damage could be high here because it's so close to a very big contact between two plates. A big earthquake would send energy close to Yuma and cause a problem there. So I figured I'd throw that in there. We're pretty good in Phoenix, right? We feel pretty confident about that. Phoenix is pretty low on the disaster scale, so if you're fearful of natural disasters, you're pretty safe here in Phoenix. Okay, so I think that's it. So take a look, make sure you read through the verbiage. I kind of glossed over some, and of course check out the links.